and screen sharing because it takes a minute to set it up. Let's do that, share. I don't have any review tonight. Okay, good. Good. All right. Oh, wait, they dropped something there. There it is. If you take a course like 232, which is quantum field theory, they'll launch you into the subject from a completely modern standpoint. And that's the most efficient way to come up to speed with modern research and so on. But it leaves a large unmotivated gap as to where this came from. And although people like to imagine that quantum field theory is somehow a different universe than quantum mechanics, in fact, the quantum field theory really is quantum mechanics, and it comes from it. So um, there's a big jump from a course like this one to 232. There was a certain point in history and physics when it was sort of assumed that the majority of people would go into particle physics, and those days are gone. But it does change the way we do things. Okay, it's about time to start then. So tonight the project is to make a beginning on the quantization of the electromagnetic field. Let me begin by addressing the electrostatic model, which is what we've used up to this point in this course for describing electromagnetic phenomena. The electrostatic model is really quite simple. We have an electric field, which is at a field point x is given by the minus the gradient of the scalar potential evaluated at that point. And the scalar potential at a point x, assuming there's a collection of particles that produce the electric field, let's sum over the particles. It's called the sum alpha, representing the particles. We have the charge q alpha, the particle, and then we divide this by the Coulomb denominator of x minus r alpha. And the notation here is that x is the field point at which the field is being measured, both phi and electric field, and r alpha is the particle position for particle alpha, and q alpha is its charge. So here's the field point here. It's x minus r alpha, this denominator. So this is just Coulomb's law, is all it is. But we frequently use it in applications in the case in which the particles are moving. And so that makes r a function of time. And we nevertheless use the same formula and just assume that phi is determined by the instantaneous positions of the particles. This is one of the approximations that goes into the Coulomb model. It's really a Coulomb approximation because in fact there is not instantaneous communication between the particles and the observation point, the x like this. There's retardation and a number of other effects. So the Coulomb model, although it's highly accurate in the circumstances that we've been using it in, omits a number of important physical effects. And those would include, for example, I just mentioned the retardation and the communication between the source of the field and the observation point. That's one. Another one is the neglect of magnetic effects that come from the fact that the charged particles are moving and produce magnetic fields. There's a neglect of relativistic effects. And finally, and most importantly, there's a neglect of the emission and absorption of radiation, which is one of the main topics that we'll be dealing with in the rest of the semester. So in order to take into account those physical phenomena, we need to go beyond the electrostatic model and go to a full electromagnetic model. Before leaving the electrostatic model, however, let me make some observations about it. You can see from these formulas here that the scalar potential phi and therefore also the electric field are functions of, they're ultimately functions, well, they're functions of x, but the x here is the field point. That's the point at which you're making the observation or making the measurement of E or phi. Otherwise, they're functions of the particle positions. So as an observable at x, or let's say just look at the electric field, as an observable at x, it's actually a function of the particle positions. And in a quantum system, those particle positions, of course, are operators on the Hilbert space. Those are quantum operators. They're also observables too. They represent the observed positions of the particles. But what this means is the electric field is really a function of the particle positions, and therefore is not an independent dynamical variable. And that's how it is with the electrostatic model. All right. Now, as I just pointed out, however, this emits a number of important physical effects. Notably, most importantly, perhaps, is emission and absorption of radiation. And in order to take those effects into account, we obviously need to go beyond the electrostatic model and to deal with the full electromagnetism in which full Maxwell's equations are engaged. So now the question arises is how do we do that? How do we incorporate the full Maxwell's equations? You know, Maxwell's equations give you differential equations for the electric and magnetic field with sources. And the sources, of course, are the charges, are the charge density and current charge. They're the charge and current densities is what they are for the matter. Matter produces charge density and current density. And those are the sources in Maxwell's equations for E and B. So one model that you might imagine is to assume that the charge density rho of x, this is the charge density, not the probability density, is the charge of the particle times psi of x squared. This would be a reasonable assumption for a charge density, and the current density, the j of x, would be equal to q times the probability density, which is the real part of psi star, the velocity operator, and psi like this, you know, using formulas that we are familiar with. So it would be possible to set up a model for the interaction of electromagnetic field with matter in which both the matter drives the electromagnetic field and the field drives the matter. Would be one in which rho and j were given by these formulas. You'd plug those into Maxwell's equations. That would determine E and B, and in turn that would give E and B as functions of time, and in turn E and B as functions of time would enter into the Schrodinger equation for psi. So you have a system of coupled equations like that. So this is a conceivable model for modeling the interaction of the electromagnetic field with matter in such a way that it would take into account the full strength of Maxwell's equations. However, this would be what you'd call a classical, you'd call it a hybrid classical quantum model, because it's one in which the electromagnetic field is treated by the classical Maxwell's equations, whereas the matter is treated by quantum mechanics. This model is actually in use. It's called the semi-classical theory of radiation. And if you ever take a course on quantum optics, you'll learn about it because it's quite useful in a number of circumstances. And it's simpler than the more exact theory, which involves quantizing the electromagnetic field. But in any case, I'm going to give it short shrift. The fact is that in this course, the fact is that these hybrid models of partially quantum, partially classical systems, partly one, partly the other, suffer from a number of difficulties, including fundamental difficulties of physical interpretation, as a matter of fact. And they really aren't very satisfactory. That doesn't mean that people don't use them. They use them, as I just mentioned, in quantum optics. They also use them in gravitational theory. In fact, the whole phenomenon of set of phenomena like Hawking radiation, which you've probably heard about, is this tells you that black holes evaporate, for example, is a hybrid, comes from a hybrid theory in which the gravitational field is classical, but the electromagnetic field is quantum. So it's another example of a hybrid classical quantum system, and it suffers from the same defects. A better approach is to quantize everything, to assume that the entire universe, not only the matter, but also the radiation, is described by quantum mechanics. This point of view is encouraged also by the measurement postulates of quantum mechanics, which tell us, amongst other things, they tell us that every observable, it's one of the postulates, every observable is associated with an operator that acts on a state space. And the outcomes of the measurements are the eigenvalues of the observable and things of that sort. So that should mean, since, for example, a magnetic field is something that's observable, let's make it a magnetic field at a definite field point. So we're just talking about measuring three numbers, x, y, and z components of the magnetic field. Those are physical observables. There's instruments you can build to measure those things. And so, in accordance with the measurement postulates of quantum mechanics, they should be associated with operators, bx, by, and bz, again evaluated at a point x. Different point x would have a different set of operators, which act on the state space and fit into the postulates of quantum mechanics. And so by thinking along those lines, you can understand some of the outlines of quantum field theory without really doing very much work. In particular, you see what's emerging here is a quantum field, as to say a field of operators. That's what a quantum field is. It's a field of operators, a different operator for each point of space. All right, anyway, we'll see how that comes out as we develop the story. Now, tonight and in the next lecture, we're going to be dealing exclusively with the classical electromagnetic field, but we're going to be analyzing it from the standpoint of how do we go from there to the quantum field? How do we quantize the classical electromagnetic field? This raises a general question, which is that if we have a classical description of a system, how do we go from there to the quantum description, corresponding quantum description? And this is a process is called quantization. It's a question to which a definite deductive rigorous answer can never be given, because it's a physical question, and quantum mechanics has physics in it. It has more physics in it than classical mechanics does. And so there is no way, there is no formula or prescription which is going to take a classical system and convert it into a quantum system and always work. In fact, at this point in history, quite notably, nobody knows how to quantize the classical gravitational field. It's one of the main areas of interest and research, which has it's not clear how much progress has been made in it in the last number of years. There's ideas that are around, but none of them are totally satisfactory. I don't think the last word has been said on this subject yet. So anyway, quantization is not necessarily a trivial subject. However, if you had to outline what the process of quantization would be like for a mechanical system, if you say, I give you the classical mechanics of a mechanical system, how do I find the corresponding quantum system? Then we can outline roughly what the procedure would look like. So let me do that now. If we have a mechanical system, we can imagine that we start with identifying coordinates on the system. We call them generalized coordinates, are usually represented by a Q. And we write down the equations of motion, which are Q double dot is equal to some function of the Q's and the Q dots. This is basically Newton's laws, F equals ma. The acceleration is on the left, put into mass if you want, and the right-hand side is the force. Generalized coordinates, these are generalized forces. So that's the equations of motion. What we then do is we look for a Lagrangian description of the system, in which there is a Lagrangian, which is a function of the Q's and the Q dots, and it may also depend on the time. I'll just leave it as Q and Q dots, such that the Euler-Lagrange equations are equivalent to the original equations of motion. And we know that this can be done with Newton's laws and many other examples of physical evolution equations. Certainly for mechanical systems, it can be done. Having found the Lagrangian, then we can carry out, again, purely within classical mechanics, a transformation which is called the Legendre transformation. And that Legendre transformation is what takes you from a Lagrangian description over to a Hamiltonian description. This is a classical Hamiltonian. And that means we get a Hamiltonian, which is a function of Q and P. But these are classical Q's and P's and therefore C numbers, meaning that the equations of motion are now Q dot is equal to dH dP and P dot is equal to minus dH dQ. These are Hamilton's equations of motion. And these, if we've done this right, will be equivalent to the original equations of motion we started out with. All right. So this sets up a classical Hamiltonian description of the system. Now then what we do is we quantize this. And the type of quantization, there's more than one way to quantize. The type of quantization I'm going to talk about is called Dirac quantization. And what it means is that the classical Q gets replaced by an operator, which is multiplication by Q, and the classical P gets replaced by an operator, which is minus I h bar ddq. And this is obviously acting on wave function psi of Q. Or if you prefer a more abstract approach, what you want is the classical Q's and P's get replaced by operators that act on the state space of the system and satisfy the commutation relations that the Qi commutator with Pj is equal to IH bar delta Ij. Those are the Heisenberg-Born commutation relations for Q's and P's. So this is the prescription which works for mechanical systems. By the way, it actually only works if the Q's and P's are rectangular coordinates. If they're spherical coordinates or cylindrical or something, then this doesn't work. It doesn't give the right, I mean, you can do it, but it doesn't give the right answers. It's known that in rectangular coordinates, it does work. And this gives us then the usual Hamiltonians that we know and love for treating quantum systems like atoms, as we've been doing in this course. All right, now my proposal for tonight is to make a beginning on carrying out a similar procedure for the electromagnetic field. However, we're going to abbreviate this somewhat. We're going to go directly from the equations of motion over to the classical Hamiltonian and skip the Lagrangian intermediary. We're going to do this for simplicity because it's possible to do this by using some guessing. And by the way, if you follow the line of above, once you got the Lagrangian, there's a rigorous procedure to get the Hamiltonian. You don't have to guess. We'll be doing some guessing because we're going to skip some steps, but they make reasonable guesses that we can check. And we'll end up with the classical Hamiltonian for the electromagnetic field. And that will more or less end our discussion of the classical field. We'll have the classical Hamiltonian for it. And then we'll move on to the second chapter, which is of this story, which is to quantize it by direct quantization and then study the corresponding quantum theory. By the way, to go back to some of the basic ideas that I mentioned a moment ago, the fact that quantities like the electric and magnetic fields become operators, or represented by operators in quantum mechanics, the other postulates of quantum mechanics come into play as well. As to say, we can expect that when a measurement is made on a system, or more exactly, an ensemble of identically repaired systems, the answers don't all come out the same, but rather there's a statistical distribution of the answers, which is governed by the rules of quantum mechanics. And we'll see that that's true, that measurements of electric and magnetic field are subject to fluctuations, which are precisely what these postulates of quantum mechanics predict. Okay,
Question.
so that's the plan. Yes, are there questions?
Yeah. So when you do this, are we assuming here that like h is like a function of q plus a function of p? Because otherwise, don't you need to like, because they're not commutative, like determine?
Yes, that's
like,
quite so.
like
And yes, that's quite so. And I'll get to that because this has to do with the ambiguities of the Dirac quantization. Because this prescription depends on the order in which the Q's and the P's are placed, which of course makes no difference in classical mechanics. I'll come back to that, but that's a good point. No, but you see, this is part of the reason why you can't make this a deductive procedure. There's no way to say, given a classical Hamiltonian, what is the quote unquote the quantum Hamiltonian? You can't do that. I mean, from a physical standpoint, that's a hopeless cause. There is a trend in mathematics in the last 30 years or so. It's called geometric quantization, and it is an attempt within a mathematical framework to, in effect, identify the natural geometrical structures that occur in classical systems, and so what they call natural geometrical structures in quantum systems, and to connect them together in such a way as to form a natural, or what natural really means here is most elegant, most symmetrical, most logically compelling, least dependent upon arbitrary decisions or conventions or whatever, procedure for doing this. And so they've done this. They've got what a procedure they call geometric quantization. But it's math, it's not physics. And it doesn't mean that if you apply geometric quantization, you're going to get the right answer. I mean, in particular, nobody has succeeded in just saying, "Oh, we'll take gravity and apply geometric quantization and get quantum gravity." That hasn't worked. All right. Anyway, If you're into math, you may know about geometric quantization, and that's my comment on it. All right, so this is the plan then. So how will we do this? Well, from this diagram, you can see the object is the place where we begin is with the equations of motion. So let's do that. So the equations of motion for the electromagnetic field are Maxwell's equations. Of course, that's what they are. And I'll divide them into two classes. I'll start out with the homogeneous Maxwell's equations. These are ones that don't have any driving terms. So this is, first of all, the divergence of B is equal to 0. And then secondly, there's Faraday's law, which is the curl of E is equal to minus 1 over C dB dt. There's no currents and charges in this, and so these are homogeneous. The other pair of Maxwell's equations are the inhomogeneous equations. And the first one is Gauss's law that del dot E is equal to 4 pi rho. And by the way, this is all in Gaussian units, which is why you see pi's instead of epsilon naughts and mu naughts. And there's Ampere's law, which is del cross B is equal to 4 pi over C. There's the current J plus 1 over C dE dt. Like so. I could make a little digression here into the virtues of Gaussian units, but I won't do that just because I don't want to spend class time on it, but it's discussed in an appendix to my set of notes. All right. Now, the homogeneous Maxwell's equations, combined with theorems from vector calculus, in particular Stokes' theorem, imply that there exist potentials, scalar and vector potential, such that the electric field is given by minus the gradient of the scalar potential phi minus 1 over C dA dt of the vector time derivative of the vector potential. And likewise, that the magnetic field is given by the curl of the vector potential, del cross A. As to say, standard mathematical theorems show that if E and B satisfy these homogeneous Maxwell's equations, then there exist A and phi such that these equations hold true. Now, if I plug these back into the equations above, they just become identities. Now, on the other hand, the potentials A and phi are not unique. Rather, they can be changed by what we call a gauge transformation. If I call A prime the new vector potential, A is given by A, the old one, plus the gradient of a scalar I'll call G. And similarly, phi prime is equal to phi minus 1 over C partial of G with respect to T. So G here is a function of X and T in general, and it's what I'll call the gauge scalar. What you'll find is that if you use A prime and phi prime instead of A and phi, the primed potentials instead of the unprimed ones, in these equations, you get the same E and B. So E and B are invariant under this transformation, which of course is what is called a gauge transformation. Now, how do we understand this physically? I like to think about it this way, is that A and phi are mathematical constructs which contain both a physical element and a non-physical element. They contain a physical element because if you compute their derivatives, you can get the electric and magnetic fields, which are measurable. This is all in the classical theory. They're measurable, physically measurable. Nobody argues about the value of E and B. On the other hand, they also contain a non-physical element because that's what changes when you do a gauge transformation. So this is a way of thinking about the A and the phi. By the way, I forgot to mention that the inhomogeneous Maxwell equations are only consistent if the current and charge density satisfy the continuity equation, del d rho dt plus divergence to J is equal to 0. And so we will assume that this is true. We'll make sure that's true in the models which we set up. All right. Now then, we can transform Maxwell's equations into equations for the potentials instead of for E and B. We don't need to do anything with the homogeneous equations because they're just identities. But if we substitute the E and B in terms of potentials into the inhomogeneous equations, we will obtain Maxwell's equations in the form of potential. So allow me to do that. I'll just run through the algebra. Del dot E is going to be equal to minus del squared phi minus 1 over C ddt of del dot A That's the left hand. That's del dot E here, and that's equal to 4 pi rho. And then for the Ampere's law, del cross B is given by the divergence of the, excuse me, the gradient of the divergence of A minus del squared A. That's del cross B term. That's equal to 4 pi over C times J for the next term, the current term, and then the displacement current becomes plus 1 over C ddt on the electric field, but the electric field is given up here, so we get minus 1 over C ddt of the gradient of phi minus 1 over C squared times the second time derivative of the vector potential appears in there. All right. Now allow me to clean these equations up. I'll change the sign of the first equation. I'll bring this complicated term over the other side. And so we'll rewrite the first equation. In fact, let me get a separate pad to put it on because I want to save it. This first equation is now going to become del squared phi equals minus 4 pi rho minus 1 over C ddt of the divergence of A. All right. And for the vector potential, let me again change the sign here: minus there, plus there, minus there, plus there, and plus there. And let me reorganize this up above. I'll start with the del squared A. We have del squared A. Then I'll get the ADT, the second time derivative term, bring it over to this side, minus 1 over C squared partial squared A with respect to T squared is equal to, then we get the current term, it's minus 4 pi over C times the current J. And then the rest of it involves this derivative, this term here and this one over here, which I can combine together to give me minus the gradient of 1 over C partial phi with respect to T plus the del dot A, like that. And let me box these then, and for a moment just call your attention to these equations. So these then become equivalent to Maxwell's equations, but written in terms of the potential. You can see they're actually rather complicated. They simplify in a covariant formulation of it, but anyway, that's what we've got. This is what they look like. All right. Now then, I'm going to save this sheet though. Let me go back to this sheet. I want to say this is a summary sheet. Now then, maybe I'll point to them. Let's see if I got enough room to do that. I'll just point to these equations up above. One of the first questions we have to answer if we're going to carry out our program, let me go back to our program here, was to start with the equations of motion. In mechanics, they were the Q double dots, is what we started with, accelerations. The question that's raised here is, what is the analog of the Qs for the electromagnetic field? Well, in mechanical systems, the Qs satisfy second order differential equations in time. Again, it's just a version of Newton's laws, F equals ma. So for the electromagnetic field, the suggestion is that the Qs are tied up in the vector potential because that's where you see second time derivatives. The Qs are not the electric and magnetic fields because they satisfy only first order differential equations in time. You know, those are Maxwell's equations. So anyway, the suggestion is that the Qs are related to the vector potential, and we will end up seeing that that's true. However, unlike mechanical systems, as I just explained, the electromagnetic field has these gauge degrees of freedom, which are non-physical, that are tied up in the phi and the A. So there's both a physical part and a non-physical part of phi and A. And how do we deal with that? Well, the way we deal with that is we use a gauge convention. Let me do it this way. Let me tear this page off. So, and to save paper and to save the planet from waste from physics classes, I'm going to turn it upside down like this. Now, so what I was saying is that there's these variables A and phi have a non-physical component, which is the part that's changed under a gauge convention. So the most convenient way to handle that is to fix the gauge, as to say choose a particular gauge which ties down the non-physical part. That's what a gauge convention is. The most obvious candidates for gauges that you can choose are either Lorentz gauge or Coulomb gauge. Lorentz gauge. Lorentz gauge, this is Lorenz, by the way, L-O-R-E-N-Z, if you read Jackson's book. In Lorentz gauge, the gauge says that del dot A plus 1 over C partial phi with respect to T is equal to 0. And this is a covariant if you put it in a covariant formulation, and that's why Lorentz gauge is favored for covariant approaches to quantizing the electromagnetic field. The Coulomb gauge is another fairly obvious choice. Coulomb gauge is one in which simply the vector potential is divergence free. We're going to use Coulomb gauge in our approach to quantizing the electromagnetic field because, for several reasons actually. I don't mean not equal to 0, it's equal to 0. Coulomb gauge is equal to 0. There's several reasons for this. A Coulomb gauge, or any gauge you want to choose, Lorentz gauge, you could say the same thing. All the gauges have advantages and disadvantages. We're going to use Coulomb gauge, so I'll tell you what it is for that gauge. The main advantage of Coulomb gauge for our purposes is that it leads to the simplest avenue for quantizing the electromagnetic field with the least amount of additional formalism that we have to learn before we get there. And for us, that's quite important because we want to get to the results. However, there's another major advantage of Coulomb gauge as well, which is that it provides us sort of on a silver platter unperturbed Hamiltonians, which amount to the electrostatic approximation, which we've been using so far this semester. The electrostatic approximation is a good one when the velocities of the particles are small compared to the speed of light, and in which the system is of a not too large spatial extent. If the system is too large spatially, then you have to worry about retardation in the communication of light signals across the extent of the system. But for small spatial extents, that's negligible. And so that's the realm in which Coulomb gauge is valid. But this is also precisely the realm in which it gets most often applied in atomic, molecular, and condensed matter physics, nuclear physics as well. And this is Coulomb gauge gives us naturally the setup for that electrostatic approximation and the Hamiltonians that we're used to using. But as we'll see, since we're going to be doing full electromagnetic theory, we also obtain all of the corrections that are necessary to incorporate all the extra physics that's contained in the electromagnetic field, notably emission and absorption of radiation. All right, so those are pros and cons of Coulomb gauge. Well, those are the pros of the Coulomb gauge. The cons of the Coulomb gauge, the negative aspects of the main one is that it's not relativistically covariant. That means if you're in Coulomb gauge in one Lorentz frame, and you transform to a different Lorentz frame, you're no longer in Coulomb gauge. Lorentz gauge is Lorentz covariance. If it holds in one frame, it holds in all frames. So what this means is the Coulomb gauge is not a satisfactory starting point if you want to achieve a covariant quantization or covariant description of the electromagnetic field. And in particular, it's not satisfactory, it's not the best place to begin for high energy processes such as things involving creation and annihilation of particles, electrons and positrons and things of that sort, and especially when you get into renormalization. The whole subject of renormalization can only effectively be done in any reasonable way by using a covariant approach. I may say more about that later, but anyway, for now, the main point is that we'll be using Coulomb gauge.
Is it easy to change gauge after you quantized the field?
You can do it. So this is a little bit tricky. And the reason is that the quantum theory that you obtain is not simply a function of the gauge, but there's also a question of the procedure that's used. And when you, and this has to do with the constraints of the system. And when you do the covariant quantization, you not only use Lorentz gauge, but you also have a way of taking care of the constraints, which is not the same as what's done in Coulomb gauge. So part of the question is, part of the answer is that there's more to the quantization than simply the choice of gauge. On the other hand, having said that, it is possible to do a quantization, for example, in Coulomb gauge, and then change the gauge without otherwise changing the quantization method. And people do that, in fact, all the time. There's ways of doing that. You go to Poincare gauge is quite useful for dealing with low energy quantum electrodynamics, emission and absorption of radiation from molecules and solids and condensed matter systems and things of that sort. So under some circumstance, depending how you set the problem, under some circumstances, a gauge transformation actually turns into it turns into a unitary transformation on the state space of the system. However, the quantization you get by using Lorentz gauge and covariant quantization is not a unitary transformation on the system we have with Coulomb gauge. It's a more complicated thing.
So does that mean there isn't one particular quantum electromagnetic field, or is one of those more accurate than others?
They are there, but the issue has to do with the handling of constraints, which is really outside the scope of this course. But in covariant quantization, one has to deal with the constraints. The subject of constraints is something that comes up in Lagrangians, especially Lagrangians with gauge invariance. This is not an issue in mechanics, so you don't see it in courses like 105, but it definitely appears in the electromagnetic field, and it's an issue that has to be dealt with in more sophisticated approaches to quantizing the field. I think that's the easiest thing to say. If you deal with vibrating strings, scalar field quantization, this is considerably simpler because you don't have to worry about gauge invariance. And that also implies that you don't have to worry about constraints.
All right, thank you.
Anyway, there's quite a story to it. If you read the first couple of chapters of a typical book on QED, I mean, there's both old ones and new ones. You'll get quite a bit of discussion of exactly these topics. Akiezer and Berestetsky is a popular choice. There's it's kind of an old book, but people use it. There's Landau and Lifshitz have a book on it. There is Rauch and Yorlik. Let's see, Jauch and Rorlich did one. There's dozens of books on the subject, more or less modern. Many of the modern books want to put it in a framework where they're also going to be doing QCD and the other quantum fields as well. So electromagnetism is just a subset of that. All right. We'll be using Coulomb gauge. I think that's the long and short of what I was trying to say in the last few minutes. So let me remove this page and let me save the equations of motion, because we'll come back to them. And what I'd like to do now is to make a digression into, let me put it over here so I won't lose it. I'd like to make a digression into the subject of longitudinal and transverse vector fields, which we need to have some machinery we need to invoke in order to understand Coulomb gauge. You may have done this in Physics 209. I would have covered it in 209. I don't know what Martin does. But anyway, I'll talk. So it might be review for you, but I'm going to cover it anyway. The subject of longitudinal and transverse vector fields. So first of all, let me begin with Fourier transforms. Let's suppose I have a vector field F in real space. I'll call it F of X. And I'll assume that the vector fields we're dealing with are real, because most of them are. I mean, this is easy to generalize to complex fields, but we're dealing with electromagnetism, so the fields are real, normally real. I wanted to find the Fourier transform by writing this as the integral over k space d cubed k over 2 pi 3 halves times e to the I k dot x times what I'll call f of k. So this is f of x to repeat this. Let me draw the line here. And so the inverse Fourier transform is that f of k is the integral d cubed x over 2 pi 3 halves times e to the minus I k dot x times f of k, times f of x. But these are just the usual Fourier transforms. There's nothing funny about it, except I'm balancing the factors of 2 pi's in the forward and backward transformations, which for the most part is a convention I'm trying to use throughout this course. One has to choose some convention, so I'm just doing this one. All right, so One notational issue is that f here of k versus f of x is really an abusive notation. I should put a tilde or something on the function of k or something indicated as really a different function. And I actually did that in the notes, but in lecture I'm probably just going to write f of k for what it is in real space, and f of x in real space and f of k in k space, because by showing the argument you get to see which space it's in. Or in any case, these are just definitions of the Fourier transform. For vector fields, by the way, you can also do this with scalar fields or any fields you want. Mostly we'll be doing vector fields. That's why I did it this way. Okay, so the Fourier transform, a couple of things to say. The fact that f of x is real does not imply that the Fourier transform f of k is real. F of k, in fact, is a complex vector field on k space. However, it satisfies the following condition that f of k, let me do it right. It satisfies the following condition that f of yeah, I'll just write this way. F of k complex conjugate is equal to f of minus k. Now this derives by virtue of the fact that the field f in real space was a real number, was a real field. And that means that in k space you have this relation. This is something that's called a crossing relation, by the way. Just given a name, crossing relation. All right, so that's one thing to note. Another thing to note is that these transformations back and forth, the Fourier transforms, the way I've normalized them, are unitary. And that means the following. It's the integral over all x space, d cubed x, of one vector field, let's call it f of x, times another vector field, call it g of x, dot product. If we transform into k space, it becomes integral over all k space, f of k, complex conjugate dotted into g of k. So with no factors of 2 pi or anything like that in here. So this obviously looks like quantum mechanics. In fact, it is quantum mechanics if you think about the mathematics of momentum space wave functions. The norm in x space is the same as norm in momentum space. And that's really all this is, but it's mathematically a property of the Fourier transform. It's called a Parseval identity, not to be confused with the opera by Wagner, which is spelled differently. Notice that it's f star g, which makes it look like a scalar product in quantum mechanics. The only reason I didn't put a star in the f is because I'm assuming that f is real. But if f were not real, I'd need to put a star in that as well. And you see, it's just a version of the usual of the usual scalar product relations in quantum mechanics. So it's easy to remember. Anyway, Parseval and crossing relations are two properties of the Fourier transform. All right, now now then, if I have a vector field in k space, f of k, like this, Fourier transform vector field in real space, we often like to decompose it into a part which is what we call longitudinal, f longitudinal of k. And this is the part that's parallel to k, plus a part I call f transverse of k, which is the part which is orthogonal to k. So to put the names down here, the first one is longitudinal, and the second part is transverse. And I'll use this little parallel and perp symbols for that. These mean longitudinal and transverse in k space. So the longitudinal part is the part where the f longitudinal is in the same direction as k. So that means that k cross f longitudinal of k is equal to 0. Whereas the transverse part is orthogonal to k, so that means that k dotted into f transverse is equal to 0. You see, geometrically, this is really simple. If I just go to k space, kx, ky, and kz, like this, and I pick a particular vector in k space, let's call here the vector k. And now I've got a field here, let's call it f of k, points off in some direction, like there. What we do is we just decompose it into its longitudinal part, which is parallel to k, and the transverse part, which is orthogonal to k. So that's the longitudinal part, and that's the transverse part. Okay. So the decomposition into longitudinal of the vector field f into its longitudinal and transverse part in k space is easy. You can just do it by dotting and crossing with k. So another way of writing this, by the way, is to say that f longitudinal of k is equal to k vector times k vector dotted into f of k. I'll put that square brackets around that and divide by k squared. Or if you want, it's k hat, the unit vector k hat times k hat dotted into f of k. You pick out the longitudinal component as a scalar and then multiply by its direction, which is k hat. And then f transverse of k is just given by, it's just the full field minus the longitudinal part. We can write it this way as identity minus k hat, which is a transverse projection operator multiplying onto the f of k. And this shows you that the process of converting from f of k to its longitudinal and transverse parts is local in k space. So say you just knowing the value of f of k at a given point, you can find the value of f longitudinal and f transverse at the same point. Now, once we've got longitudinal and vector fields in k space, we define the corresponding fields in real space. And we do it this way, is we just simply declare in real space that f of x is equal to f longitudinal of x plus f transverse of x. Maybe I'll pause here for a minute and just say, don't lose track of the forest for the trees here. We're setting up the Maxwell's equations, and we decided to use Coulomb gauge. Coulomb gauge says that del dot A is equal to 0. And what I'm doing now is I'm going on to a fairly big digression into the subject of longitudinal and transverse vector fields, so that we can talk intelligently about the Coulomb gauge condition and go back to that and then deal with Maxwell's equations. So I'm in the middle of giving you this elaboration on the meaning of transverse and longitudinal vector fields, and then we'll go back to the Maxwell's equations and the more physical stuff. So when we talk about the longitudinal and transverse vector fields in real space, what we mean is that f longitudinal of x is the inverse Fourier transform of f longitudinal of k. Or to put it another way, if I wanted to compute the longitudinal component of x in real space, given the original field, I would take the original field, I would Fourier transform it to find f of k. I would then get the longitudinal component of that by using this formula here, get f longitudinal of k, and then I would Fourier transform back to get f longitudinal of x. That's how this would work. And I do something similar for the perpendicular part, or if I have the transverse part. Of course, if I have the longitudinal part determined, then all I have to do is subtract that from the total field, and I get the transverse part. Anyway, that's what it means in x space. Now, the operator gradient in x space corresponds to multiplication by ik in k space. You can see that just from the Fourier transform here. Here it is. If I just apply a gradient to the f here, it's just going to bring down an ik from this exponent over in k space. So this is an obvious rule here. In any case, because of this rule, this means that because k cross f longitudinal is equal to 0 in k space, it means that del cross f longitudinal in real space is equal to 0. And likewise, because in k space k dot f transverse is 0, it means that del dot f transverse of x is equal to 0. And so what we have here is a version of sometimes called Helmholtz's theorem. It says a quote unquote arbitrary vector field f of x can be decomposed into two terms, one of which is curl free and the other of which is divergence free. I say quote unquote f because if you want to state the theorem rigorously, you have to worry about the boundary conditions on f. In particular, the simplest way to make the theorem come out right is to assume that the vector fields that we're talking about vanish at infinity. And so if there's any question about boundary terms, we'll make that assumption about these fields. That means that boundary terms that arise when you do integration by parts can be discarded. And that allows you to prove these theorems here. If the fields extend all the way to infinity and don't vanish, then the problem becomes somewhat more complicated, slightly more complicated. All right, in any case, so you get these theorems about vector calculus from this. All right. So the longitudinal part is curl free and the transverse part is divergence free. And now what you can see is that because of Coulomb gauge that we're using, del dot A is equal to 0, In Coulomb gauge, this means that A is actually purely transverse, that A has no longitudinal part. In Coulomb gauge. In other gauges, it would. By the way, something, oh yeah, here's another thing to say too. You can see that the gradient of a scalar, if S is a scalar, let's say S is a scalar, then you can see the gradient of a scalar is purely longitudinal. Why? Because its curl is equal to 0. Likewise, if I have V as a vector, then the curl of V, del cross V, is purely transverse. And how do I know that? Because because the divergence of the curl is equal to 0, and so that makes it a transverse vector field. All right. So okay, so those are some facts about longitudinal and transverse vector fields. Let's see here. I think there is just one more thing that I want to say. Let's suppose I have two vector fields, f of x and g of x. And let's suppose I convert them into their Fourier transform, so I get f of k and g of k. Okay. Now, let's suppose that f is purely longitudinal. And let's suppose that g is purely transverse. If that's the case, then f of k, f longitudinal dotted into g transverse is equal to 0 because they're orthogonal to each other in k space. This is true at each k value, each point of k space. Does that mean that in x space, that f longitudinal is orthogonal to g transverse at every point of x space? The answer is no, it's not true. And the reason is that the Fourier transform is non-local. There's a non-local condition. However, what is true, by virtue of Parseval, what is true is that the integral d cubed x of f longitudinal, the longitudinal part of any vector field f, dotted into the transverse part of any other vector field g, by Parseval, this is equal to the integral over k space of the same kind of an expression, except in k space. And I'd put a star in here now, dotted into g transverse in k space. But the integrand on the right-hand side is strictly equal to 0, so the right-hand side is equal to 0. So, although longitudinal and transverse vector fields in real space are not orthogonal to one another, if you take their dot product and integrate over all of space, the answer is 0. Let me put it this way. This is the corollary of the Parseval identity for longitudinal and transverse vector fields. All right, now, something we need to do from time to time is that, say, given an arbitrary vector field f of x, we want to find the transverse part of it. And the question is how to do it. How do we do it? And I'm going to show you two different methods of doing this. This leads to what's called the transverse delta function, which is something that we'll need to use. So let me clean up the pile of pages here. So I need to use something called the transverse delta function. So as I just explained, given f at x, you can't, there's no local operation that will allow you to determine f perp at x. Unlike in k-space, there's nothing local. However, it turns out there's a global operation, as to say the transverse component of f at a position x depends on the values of the original field f at all other points of x space. So we get an expression that looks like this, is that f perp, or f transverse of x, is equal to an integral transform, t cubed x prime, of a certain kernel, which I'll write this way, is delta transverse, and I'll put double arrows over it because it's actually a tensor, of x and x prime. And this tensor is dotted into f evaluated at x prime. So this is a definition of this kernel here, which is called the transverse delta function. And I call it capital delta because people like to call it a delta function. But anyway, other people have other notations for it, but this is it. So this is a tensor, which means if I multiply by a vector, I get a vector here. It depends on x and x prime. And you see it plays the role of a kernel of an integral transform that takes you from f over to the f transverse. And shows you that the values of f transverse are non-local. They depend on f, the original f, everywhere in space. Okay, so let's work out expressions for the transverse delta function. I'll begin with the easiest way of doing this. This is just to follow the formulas around. Let's take f transverse of x. This is equal to, by our definition, it's equal to the Fourier transform of the same thing in k space. So I'll write that out, e to the I k dot x times f transverse in k space. But f transverse in k space, switch to red ink, bring it over here, is equal to the identity minus k hat multiplied onto f in k space without the transverse. This first factor here is the transverse projector in k space. The k hat projects out the longitudinal part. We just, the identity just does nothing. Subtracting the two gives us the transverse part. Now then, the f of k, which appears here, however, bring that down, is given by the Fourier transform of the original field. So it's d cubed x prime e to the minus ik dot x prime times the original vector field f evaluated at x prime. And I'm using a prime in the x's here because I don't want to confuse it with the x, which was the point at which the original f was evaluated. So what I want to do is to put just follow these red lines and just put all this together, and then use it to up here just to read off what the transverse delta function is. Basically, the transverse delta function is the entire right-hand side of this. If I cancel out the x prime integral and cancel out the f of x prime, so the x prime integral, to use my red pen again, is right there, and the f of x prime is right there. And the rest of it's going to give me the transverse delta function. So if I do that, what I get is delta function transverse. As I say, it's really a tensor. It depends on x and x prime. And it's equal to, there's k integral survives, integral d cubed k. There should have been a 2 pi 3 halves here in this inverse Fourier transform. So actually it's a forward Fourier transform. There's one here and one here. So I get a 2 pi cubed altogether for those. Then the phase factors become e to the I k dotted into x minus x prime. And then the only thing that's left over is the transverse delta function I minus k hat. So let me box that because that's a useful expression for the transverse delta function. And you can see in particular, it depends only on the difference between the points x and x prime, because that's where it appears here. You can also see that it's essentially the Fourier transform of the transverse projection operator in k space, kind of not such a surprising conclusion. All right. So this is one way of getting the transverse delta function. I'm going to give you another way of doing it, which is also, it's educational to do it two ways. This is taking you through the kind of vector calculus you use in electromagnetism in a fairly standard way. The second approach for getting the transverse delta function is going to be to work strictly in x space and don't go to k space at all. Let's do it this way. Let's take the f of x. Let's take f longitudinal of x for starters, f longitudinal of x. What we know is that the curl of f longitudinal of x is equal to 0. Now this implies, again by standard theorems of vector calculus, that f longitudinal of x must be equal to the gradient of a scalar. I'll call it lowercase f. And I'll put a conventional minus sign in front of it so it looks more like what you're used to with electromagnetism, as if lowercase f is a potential. Now, to solve for lowercase f, we need to take the oh, let's see. What was I going to say? F del cross F is equal to 0. Yes, here's what I want to do. I want to take the divergence of both sides of this equation. So I get del dot of F longitudinal on the left-hand side of X. This is all of X. This is all in X space. However, the total F is F longitudinal plus F transverse, and divergence of F transverse is equal to 0. So this is the same thing as the divergence of the original vector field F of X. And that's equal to the minus sign now to the Laplacian of F. So if the original vector field F of X is given, we're assuming that we want to get the transverse part, then we can compute its divergence. And so this left-hand side is known. And so what we get is a Poisson equation for the unknown scalar F. I can turn this around if you prefer to make it look more like the Poisson equation. It looks like this, del dot F of X. So it's like the del dot F of X looks like a charge potential, excuse me, a charge density, and F is the potential. So the solution is that F of X, and this is a unique solution that goes to 0 at infinity, F of X is equal to using the Green's function for the Poisson equation, it's 1 over 4 pi integral d cubed x prime of del dot F of X prime divided by the Coulomb denominator x minus x prime. Okay, so we can solve for the scalar F such that its gradient minus gradient is equal to F longitudinal. So you can see the strategy now. We can solve for F. We take its gradient. We're going to get F longitudinal. We just subtract that from the original F, and that'll give us F transverse. So that's the idea. But anyway, it's worthwhile to work it through. Now, one thing here is this del dot. I should really write it as del prime dot because this is evaluated at x prime. And I want to take the divergence with respect to the primed x. There's the other x, both x's are here. There's two of them. You need to be careful about the distinction between them. Also, let me take this integrand and integrate or write it by, essentially integrate by parts. Use vector identity. I'll write this as the gradient of, it's really a prime gradient of 1 over x minus x. Oh, no. Here's what I want to do. I want to do it this way. I want to write it as the prime divergence of f of x prime divided by the Coulomb denominator x minus x prime minus the prime gradient of 1 over x minus x prime dotted into f of x prime. This is essentially aiming for an integration by parts on that integral. By Gauss's law, the first term is going to go away. Strictly speaking, to make that happen, we need to assume that f goes to 0 to infinity, and we will make that assumption. If so, the boundary terms go to 0. And so by Gauss's theorem, this term goes away, and what's left over is the second term. You see, in a sense, what we've done is we've shifted the del prime from the f over to the Coulomb denominator. That's all this is done. All right. Now, another thing to say is that the Coulomb denominator depends on the difference between x and x prime. So the del prime in this context is the same thing as minus del. Those operators have an effect which is just opposite one another. And so I can put this together then. And what I get is an expression for f of x, for the scalar f of x, which is equal to, these two minus signs will cancel, so I get an overall plus 1 over 4 pi. Signs are tricky here, I hope I do it right. D cubed x prime. And then I have the unprimed gradient of the Coulomb denominator. That's, of course, like an electric field, dotted into f of x prime. And you see where I'm aiming at. I'm aiming at an expression where I've got an integral transform, and the f of x prime is what's being transformed. And on the left-hand side, we're going to get f transverse. So this is building this up. This then implies that f longitudinal, which is minus the gradient of f, is equal to minus 1 over 4 pi times the gradient of this same integral. Let me just write it out. Again, just copy it, d cubed x prime del of 1 over x minus x prime, the Coulomb denominator, dotted into f of x prime. And therefore, f transverse of x is equal to f of x minus this f longitudinal. Okay? Now, it is convenient, however, to write the entire right-hand side as an integral transform. That's what we want for the transverse delta function. If you'll recall, let's see if I still have it here. It's right here. This is the kind of an expression we want. We want the whole thing to be an integral transform. So we need to take this first thing, which is kind of an identity, and turn that into an integral transform as well. And so we'll do it in the following way. We'll write this as the integral d cubed x prime of a Dirac delta function of x prime, Dirac delta function of x minus x prime. Am I still on the page? Yes. Multiplied by the identity tensor, dotted into f of x prime. And so now both terms are integrals like this, and with f of x prime on the right-hand side. And if I put this together, what I'm going to get is, what I end up getting ultimately is the following. Oh, by the way, and then here's something else too. Let's take this delta function, which is in here, and this is doing some reverse engineering here. Take this delta function, we'll write it as minus 1 over 4 pi times del squared of the Coulomb denominator. All right, using well-known identities. So this is kind of messy, but if I put it all together in order to write it into this following form here with the transverse delta function, the answer comes out to be the following. This is the transverse delta function, and I'll write its components, ij components like this. It depends on x and x prime, and it's equal to minus 1 over 4 pi. And then we have this operator, which is delta ij times the Laplacian minus the second derivative with respect to xi and xj applied to the Coulomb denominator 1 over x minus x prime. And this is a second useful expression for the transverse delta function. Here's the first one right here, the Fourier transform. Here's the second one, like this, written out explicitly in X space. It's now not a Fourier transform. It's just involves derivatives. Okay, so I'm going to just post those as results, which will be used later on, and this is part of an elaboration on the subject of longitudinal and transverse vector fields. All right, now then.
Can I ask a question?
Yes.
So this transverse delta function, it's just a matrix, right? It's not necessarily like any higher rank of a tensor.
Yeah, it just has two indices, because the idea is you multiply it by the vector under the integrand, and that gives you another vector.
Okay.
So you might look at it this way: is the integral transform, of course, means integrating over the x dependence of the vector field. But the vector field also has an XYZ and a component 1, 2, 3 XYZ dependence, and so there's a linear transformation in that as well. That's why there's effectively a matrix in those variables.
Okay, thank you.
So this finishes all I wanted to say about this rather lengthy digression into the longitudinal and transverse vector fields. So are there any questions about that before we go back to talking about Maxwell's equations?
Yeah, should we just a way to view it? Should we view the transverse delta function as like the projector onto divergence-free vector fields?
Yeah.
Let's see. It seems like this is what this is.
That's what it is. It's a projector on it. Takes the original vector field and throws away the exact curl and ends up with the exact throws away the exact divergence and ends up with the divergence-free part. That's what it does. Okay. All right. Now what I'd now like to do is to go back to the field equations, and I saved them, as you'll recall. So let me look through my notes here and find where we saved them. Saved them for a reason. And now I can't find them. What did I do with them? Just a minute. Let me make sure I'm doing this right. What happened to them? Oh, I know. I put them over here. I put them in a safe place. That's why I couldn't find them. All right. So here's the Maxwell's equations written in an arbitrary gauge. What I'd like to do now is to specialize this to Coulomb gauge, because that's what we're going to be using. And I'm going to say that again, that A is equal to A transverse in Coulomb gauge. There is no longitudinal, or I put it another way, is A longitudinal is equal to 0. By the way, if you do a gauge transformation, recall that A prime is equal to A plus the gradient of G. However, I've also pointed out that the gradient of a scalar is always purely longitudinal. This is purely longitudinal here. So what a gauge transformation does for any gauge, going from any gauge to any other gauge, what it does to the vector potential is it changes the longitudinal part of the vector potential, but not the transverse part. And Coulomb gauge amounts to setting the longitudinal part equal to 0. So what this makes it more clear that the choice of Coulomb gauge is in effect a step. So okay, back up a little bit. So since the gauge transformation changes the longitudinal part, but not the transverse part, the longitudinal part is the non-physical part of the vector potential, whereas the transverse part is the physical part. And when I set when I set A longitudinal equal to 0, which is what Coulomb gauge is, it's establishing a convention for the non-physical part. Basically, it sets it to 0. That's what it does. So this is a way of looking at it, which I think is useful. It makes it more clear about the breakdown. All right. Here's another point to make, is that the electric field in any gauge is given by minus gradient phi minus 1 over c dA dt. But the gradient of a scalar is always purely longitudinal. And if we're in Coulomb gauge only, then the ADT term is also purely transverse. So what this means is that we can write E is equal to E longitudinal plus E transverse. You can do that for any vector field, but what we find is that E longitudinal is minus gradient phi, and E transverse is equal to minus 1 over c dA dt. These are results that hold only in Coulomb gauge, but that's useful to do because in the electrostatic approximation, the electrostatic component of the electric field is the dominant one, and the transverse part is small. In fact, that's what the electrostatic model involves, is neglecting the transverse part. I'll come back to that later on, but in Coulomb gauge, the two terms for the expression of the electric field are precisely the longitudinal and transverse components of that electric field. All right, in any case, let's just simplify Maxwell's equations when del dot A is equal to 0. So that term goes away and that one goes away. Let's write them out here. So we get del squared phi is equal to minus 4 pi rho. And we get del squared A minus 1 over c squared d squared ADT squared. It's basically a wave operator on the vector potential. Is minus 4 pi over c times the current density J plus another term, which is minus 1 over c ddt of the gradient of phi. Let me box these because these are the equations in Coulomb gauge. They've simplified. All right, let me save this piece of paper. Actually, I'm going to save this piece of paper in a minute, but I want to make a few more comments here. One of the comments about these equations in Coulomb gauge is really quite interesting. Again, this could all be in 209. If you look at the equation for phi, you can see it's nothing but the Poisson equation. And we know how to solve the Poisson equation from electrostatics. The solution is given, the unique solution which vanishes at infinity, assuming the charges are localized, the unique solution is that phi of x and t is equal to the integral d cubed x prime of the charge density rho evaluated at x prime and t divided by the Coulomb denominator. I'm allowing phi and rho to depend on time because we're doing full electromagnetism here. We're not doing any electrostatic approximation. We haven't made any electrostatic approximation, and we don't want to because we want to get the full electromagnetism out. These equations in Coulomb gauge are rigorously equivalent to the original Maxwell's equations. However, the scalar equation is solvable using the Green's function for the Laplacian, otherwise solving the Poisson equation, and here it is. Now, the interesting thing about this equation is that the scalar potential at a field point x and at time t is given by all the charges in the rest of the universe at positions x prime, evaluated, given their locations at the same time t as the observation time. In other words, this equation this equation has no retardation in it. It's as if the charges communicate instantaneously at the speed of light to produce the scalar potential. That's what it looks like in Coulomb gauge. Well, it is what happens in Coulomb gauge. And so the question is does this violate physical causality? The principle that causality usually means in relativity theory usually means that signals cannot travel faster than the speed of light. And the answer is no, and the reason is because you can't measure phi. Phi, even classically, is not measurable. It depends on the gauge convention. That's why. What is measurable is the electric field. And the electric field is the sum of the longitudinal and the transverse parts. The longitudinal part indeed is given by the gradient of phi, but that's not what your electric meter is going to measure. It's going to measure the total E, including the transverse part. So now it turns out so now it's obvious that the longitudinal part of the electric field, just like phi itself, is not retarded. However, the total electric field must be properly retarded. And therefore, the transverse electric field must contain both a retarded part and a non-retarded part in exactly such a way that the non-retarded part cancels out the non-retarded part of E longitudinal. And this, in fact, is the case. There's going to be a homework problem in this in which you get to explore this in more detail. But this is the case. The causality can only be seen if you look at the total electric field and not this decomposition. Nevertheless, this decomposition, in which E longitudinal is given by the instantaneous gradient of the instantaneous non-retarded scalar potential, is exactly what we've been using up to this course in the electrostatic model. So in effect, what we've been doing is ignoring or been treating E transverse as small, which it is under the circumstances we've been looking at. But it's important to include it if you want to see the effects of retardation. All right. So using Coulomb gauge and this formula for the scalar potential does not violate relativistic causality because phi that you see here is not observable. That's the main point that needs to be made about these Coulomb the wave equation, the Maxwell's equations, field equations in Coulomb gauge. All right. Now I have a few minutes left, and what I need to do is to start another digression into some formalisms we need in order to construct this theory. And the next one has to do with a periodic boundary conditions. And I don't think this is too hard to do because we've done it before when we were doing scattering theory. We're going to introduce periodic boundary conditions, i.e. we're going to divide the universe up into an infinite number of boxes of equal size. We'll call the length of the box L, and we'll call the volume of the box B equals L cubed, just like we did before. And we're going to imagine that all of the physics, including the radiation as well as the matter, is periodic in these boxes. And the reason we're going to do this is because we want to start talking about the modes of the electromagnetic field. And by putting it in boxes, we get discrete modes, which is convenient for analysis. It's convenient especially for an introduction to the quantization of the electromagnetic field, is to have a set of discrete modes rather than a continuum of modes. So that's what we're going to do. This means, of course, that we need to let the volume go to infinity at some point in order to get physical answers, just like we did in scattering theory. By the way, sometimes electromagnetic fields actually are in boxes. They're called resonant cavities, and they're used a lot experimentally for all kinds of purposes. They're called waveguides and cavities and so on. And there's a whole sub-branch of quantum electrodynamics called cavity QED, which you may well learn about if you go into certain fields. So the use of boxes here is not necessarily purely a mathematical crutch, but there's physical circumstances where it actually appears. In any case, for us, it's mainly going to be a matter of making the modes of the electromagnetic field discrete. So we've seen the details of the box normalization in the past. Since all the physical quantities are now periodic, it means they're not expanded in Fourier integrals, but rather in terms of Fourier series. For example, if S of x is a scalar field, which, as I say, we'll assume is periodic, we can write it as a Fourier series where we sum over k values of coefficients I'll call S sub k times e to the I k dot x. And the k values are the same ones we saw before, as k is equal to 2 pi divided by the length of the side of the box times an integer vector n, which is nx, ny, and nz. Where these components in the integer vectors are integers, they belong to the set the mathematicians write is blackboard z like this. This means all the integers positive, negative, and 0. And as I've explained in the past, this means that the quantized k values create a square lattice, cubical lattice of points in k space. This lattice has a certain density. It's really a density of states in k space, which is equal to the volume divided by 2 pi cubed. This is the volume of the box in real space. So that you can see that as the volume goes to infinity to get physical results, the density of states goes to infinity as well. Again, this is just a repeat of what we had before. What we have here is an example of a Fourier series for a scalar field. I'm going to adopt the convention that we'll split off a factor of 1 over the square root of the volume up front for convenience. It's just convenient to do that. This obviously just changes the definition of the Fourier coefficients S sub k, but we'll take this then as our definition of Fourier series. Just a couple of comments about the Fourier series. One of them is the crossing relations, is that if S of x is real in real space, then what we have is in k space, we have S of k is equal to S of minus k complex conjugate. Excuse me, it's not a vector here, it's a scalar. Complex conjugate. This is the crossing relations. And we also have the Parseval identity, which I'll mention here. I'll write this in terms of a vector field. It's the integral over x space of a vector field f of x. I could do this for scalars. I'm just going to do it for vector field. F of x dotted into g of x. Two vector fields dotted in together, integrated over all of x space. This is equal to the sum on k of f sub k dotted into g sub k. And we need to complex conjugate the f because the Fourier coefficients in general are complex. We complex conjugate this too if f were not necessarily assumed to be real. Then of course you wouldn't have the crossing relations. Okay, so this takes us up to pretty much finishing, I think, what I want to say about just mark down here how far we got. So this is all for tonight. We'll continue this next time, and I'm sorry about the big digressions into various kinds of technical formalism, but we'll get to apply all of this in the next lecture to constructing the Hamiltonian and conjugate Q and P variables for the electromagnetic field, and then we'll be prepared to do the Dirac quantization to convert it into a quantum field. Are there any questions about the lecture tonight? If not, then we can proceed to stop screen share. And then we can pause the recording.